Now in chapter 5, we move on to the famous multi-layer perceptrons, which is basically, which is the basics of all these more complex networks, feed-forward networks that are used in the community. So this is getting now a bit more complicated. And as you can see from the table of contents, we are starting with a brief introduction and motivation. So why do we need these kind of networks? How are they defined in their basic form? How do we learn in these more complex architectures containing nonlinearities? We formulate the error backpropagation algorithm. And then we look into two examples, the famous XOR problem that we already met when we were talking about the perceptron and what McCulloch-Pitts did. And we have another example, a simple one that considers a regression problem. The next part of this chapter is called structural considerations. And in this section, which contains several subsections, we are looking into structural problems and things to know when we are working, when we are doing machine learning. So many of these considerations apply to almost all of the machine learning methods. And the second part, the next part will be algorithmic considerations. Here, this is more specific towards the error backpropagation algorithm and what's known as gradient-based learning. And in the end of this chapter, we again focus on so-called cross-entropy error functions, which are the error function that is used for classification purpose when we have multiple classes. So this is what's ahead of us in chapter 5. And after chapter 5, there is this chapter 6, which then focus on a more specific feed-forward multi-layer perceptron with more restricted connectivity and so on. So this is the general setup of these multi-layer perceptrons. Okay. So let's start with introducing multi-layer perceptrons, what they look like, and what their properties are. Nope. Here we go. Right. they have changed something in the Zoom version. So sharing of screen is now kind of unpredictable. So you don't see all the screens that are available. I'm not sure if I am doing something wrong, but this has changed short before Christmas, and I had no problems before that, so I'm not sure what's going on. Okay, anyway, let's start with the introduction. So in chapter 3, we started to look at learning and so-called discriminating between classes. And the first thing we did was we introduced the perceptron with the perceptron learning rule. And the second model we focused at was the ADA line, the adaptive linear element. And the learning approach in both models is kind of, it's different, as you remember. Both models work well for linear separable data. The perceptron only works for linear separable data and approximately linear separable data. So data that has a more or less linear decision boundary. Unfortunately, as you can imagine, many problems that we are trying to solve with machine learning are not linear separable at all, not even close to being linear separable. We've seen a lot of examples already. So we had the example where we were discriminating letters A and B by width and height of the bounding box. And when we looked at this Bayesian modeling where we said, well, there's a distribution of width and heights for A's and width and heights for B's, we saw that there is an overlap between these classes, right? And it depends on the writer how good the classification will be. We also seen these object classification tasks where we had the scissor and the cup. And basically, you can distinguish between scissors and cups, again, using the bounding box and trying to classify them according to the geometry of the bounding box. But the bounding box basically depends on the angle that you are looked at the different objects. So this is something that's probably not linear separable. And we've seen in the morning that even for this 7-segment display, which is pretty easy and there's not much noise involved in the setting, even for this simple example, we do have we can easily generate classification tasks that are not linear, that are non-linear separable. So, to summarize it, complex problems usually do not satisfy the condition of being linear separable in the beginning. So the question is, what can we do? And there is an idea, which is involved in multi-layer perceptrons. And this idea is that we do a clever combination of a number of nonlinear processing steps, or we use a number of nonlinear processing elements such that in these processing elements transform our originally nonlinear separable problem into a linear separable one. So when we look at the architecture of multi-layer perceptron. So on the right-hand side, we do have our inputs x1 to xk, right? And then we have a hidden layer, which consists of a number of nonlinear processing elements, neurons, right? And these neurons are transforming the original problem into an output vector. And I called it white twiddle, that is linear separable. So the output neurons in the output layer, they look now at a linear separable problem and can do the classification using the mindset or what we've seen for the perceptron and the ADA line model. So the idea that's contained in this approach, taking a nonlinear separable problem, doing a nonlinear transformation and transforming it into a linear separable problem. This idea is supported by a theorem that can be proven, which states that the probability of having or getting linear separability increases if you apply a nonlinear transformation to the original data. So we will come back to this theorem when we do structural considerations. We look a bit closer to this theory. But this is the basis of the idea behind multi-layer perceptron, and this is also the reason why they are so successful. Okay, so let's do a more formal definition of multi-layer perceptrons. So the concrete definition, and we are using a basic type of multi-layer perceptrons. So we use a neural network that consists basically of 3 layers. And to be honest, there are 2 functional layers. The input layer is usually a layer that just takes the input data and outputs the input data again. So this is just a sort of notation that has not much function. It becomes interesting with the hidden layer. And so we have input layer that contains of K neurons, and these K neurons just get 1 input and 1 output, and the output is basically equivalent to the input. So that's how we define the input layer. So this means that the hidden layer gets the input values, right? So we have this hidden layer, and we introduce another variable here, or another letter, which is J. So J is the number of neurons in the hidden layer. And then we have the output layer, and we will consider I neurons in the output layer, right? So we have a hidden layer, and so the output of the hidden layer can be interpreted as a vector S, which contains J real numbers. And the output of the network is the output of the I output neuron, so we can interpret it as a vector in I-dimensional space. So overall, if we summarize the function that's calculated by this network, we have the input, which is k-dimensional, and we have the output x, and we have the k-dimensional input x, and we have the I-dimensional output y. And in between, we have a hidden representation, which is S, and this has dimension J. Okay, so this is the overall setup of a multi-layer perceptron containing 1 hidden layer. Let's focus now a bit closer on the individual elements in the hidden and the output layer. In the hidden layer, we have formal neurons, and we have J of them, right? Which have weights, and these weights are denoted WKJ because we have K inputs to each of these hidden neurons. We have a threshold W0J. This is the threshold of the J's neuron. And we have our integration, and in the hidden neuron, we are applying the sigmoid activation function, right? F1. So what we get, the output of our neurons in the hidden layer are real numbers, which are element of the open interval between 0 and 1, because that's the domain, that's the range of the sigmoid transfer function.
Professor?
Yeah?
I have a question, yes, to the slide, or to the formal neuron below. And I have a question because we have our inputs x1 to xk with k neurons, and
neurons in the hidden layer do see the complete input space, so they get input from.
My question is the hidden layer, the hidden neurons. In the neuron, where are they get the function? Where are they used to prepare it? You know what I mean? How it looks like, because my K neurons, I get inside. This is my input, and they get addition. Yes. And after that, comes my hidden neuron, or how they calculate it.
The hidden neuron, basically, in the morning we saw the perceptron.
Yes.
The activation function of the perceptron is what?
Yeah.
What's the activation function of the perceptron? The
This
sign function. So F is the sign function.
This is signum.
Huh?
Signum.
Here we do have, yeah.
-1 and 1.
Yeah.
Yes, this is a signum because we have a linear separation. And here we
have the sigmoid logistic function.
Yes, okay, I understand what you mean. Okay, thank you, Professor.
But the calculation is basically all the same.
Okay, thank you.
We just have J neurons.
Okay, thank you, then I understand.
All right. So it's just a bit more complicated, a bit more neurons. All right, so this is the hidden layer. So it consists of J neurons, and each neuron looks like this, given our initial graph-like representation. The neurons in the output layer are slightly different. They do get inputs from the neurons in the hidden layer. So they get J inputs, each of the neurons in the output layer. And we have also weights in the neurons in the output layer. And to have a distinction between weights of the hidden layer and weights of the output layer, we are using the symbol V for the weights of the neurons in the output layer, just to distinguish. Otherwise, we would have to include another superscript or something else to have the distinction between layers, between weights in individual layers, right? So we have VJI. These are the weights for the individual outputs of the neurons in the hidden layer, which feed into the neurons of the output layer. And of course, each of the neurons in the output layer does have a bias, right? And this is V0I. So we have the integration part, and in contrast to the neurons in the hidden layer, we are assuming linear output function for the output, linear activation function for the neurons in the output layer. So, and each neuron in the output layer outputs a real valued number, yi. So this is how the details of the neurons in the hidden and the output layer look like. So, and as you can see, here, the sigmoid logistic activation function here, this is the nonlinearity. This produces the nonlinear transformation. Okay, everything else is linear. Okay, look a bit closer to it, even more close. So these are the neurons in the hidden layer, and we have this IO activation function, which has this shape. So it got for arguments which are with very negative arguments. The output of the neuron is 0. For very positive arguments, the output is 1. And there is a smooth or a nonlinear transition here, a more or less linear transition for arguments around 0, and a nonlinear mapping for before it approaches the maximum output of 1. So this is the formula of the sigmoid activation function that we introduced in the beginning of the lecture. The output function of the activation function of the neurons in the output layer is linear, so it just outputs the inner product of the weights times the inputs from the hidden layer. Okay, in terms of formulas, we know here we have the weight vector of the J's neuron transpose times the input value. And this is the argument to the sigmoid output, sigmoid activation function, and this is used to calculate the output as J. We can summarize all the weight vectors of the neurons in the hidden layer in a matrix W. So we use a column-wise representation. So we have a K by J matrix. So we have K rows and J columns, and if we transpose this matrix, multiply it with the input vector and apply the activation function for single matrix elements, because this is the output of the neurons, we get a vector value, we get a vector representation S, which is a J-dimensional vector. We can do the same thing for the output vector. We can summarize the weights of all the neurons in the output layer into a matrix. So we have a J by I matrix. So we have J rows and we have I columns, and using the transpose of this matrix, multiplying it with the output of the neurons, the vector that summarizes the output of the neurons in the hidden layer, we get the output Y, which is an I-dimensional vector, and this is the output of our network. Okay, so this is basically what you should be aware of when you understood what we've discussed so far. Okay, so in total, if we now formulate the mapping function of the network that maps X to Y, we are calculating the individual output by applying the weight vector of the ith output neuron transposed times the output of the neurons in the hidden layer. And we can even write this more condensed, so the complete output of the network is given as V transpose times the sigmoidal activation function applied to the transposed weight matrix of the hidden neurons times the input. And as you can see, there's exactly one nonlinearity involved in this calculation, and this is the activation function of the hidden neurons. So we want to consider this feed-forward neural network as a general framework for representing any kind of multivariable nonlinear function that maps a set of input variables in k-dimensional space onto a set of output variables in i-dimensional space. So for most of the discussion in this chapter, we are using this standard configuration of a so-called fully connected feed-forward network with one hidden layer. In the next chapter, which is called convolutional neural networks, you will see an example of a feed-forward network that has multiple hidden layers. But in this case, we have a more restricted connectivity and a more structured connectivity. You will learn about it, right? So it's not fully connected. The CNNs are not fully connected. But in this chapter, we stay with this very general notion of or model of a multi-layer feed-forward network. Okay. So this is the architecture. Are there any questions? We had the question about implementing the hidden layers. Any other questions? Maybe something I missed to explain because it's obvious to me but not obvious to you. All right. So let's move on. So this was the architecture, the model definition. So the next step that we are taking is how do we learn in these? How do we learn with these models? So how do we learn the weights of the output neurons, the VI, and the weights of the hidden neurons, WJ? So let's first define what we do have in this case. Because we introduced in the introduction, I referred to perceptron and Ada line, and these two learning algorithms are so-called supervised learning algorithms. So they have, so for these learning, we do need labels. So what we assume here is we have training data that has labels. So we have pairs XQ, TQ, which give us the problem we want to learn in terms of given target values that we want to approximate. And we have Q training samples. The input data XQ is, of course, k-dimensional. The target values TQ are i-dimensional if we stick with the representation of having I outputs. So the learning task is given, so we have the network that we introduced right now. So we have X and we want to map it to Y, which is a function of X, and we have derived the formula how we calculate Y of X. So what the network should learn is that when we present the input XQ, it should deliver Y of XQ that is as close as possible to the target value set that is given for this particular XQ that we know TQ. So this is what we want to do, that the output the network calculates is more or less equivalent to the given target value TQ. Or in other words, what we try to do, we want to try to minimize the distance between the generated output of the network, YXQ, and the given target value TQ. So basically, this means that we have to formulate a kind of a distance function, and that evaluates how how good the generated output is when compared to the given target value. Okay, and this is in the literature or in the community. This is either called error function, loss function. What else? I think in the recent times it's called loss function in most of the papers, but still error function makes sense because we are introducing an algorithm that's called error backpropagation. So I prefer error at the moment. Okay. So when we look at the problem, since we have multiple parameters involved, and more importantly, we have a nonlinear activation function now, it's very hard to give a closed form solution for this optimization problem. So the approach that we are taking is the same as we did in chapter 3. We apply an we find the solution by an iterative method. So we are updating the weights step by step. So we calculate new weights based on the old weights, or on the weights that we do have currently that already have learned a bit of the problem, and we are adding an update to these to the current weights, which is usually a function h, which is based on the current weights and the input data x, and we apply or we multiply this update that we are calculating here with learning rate alpha. We have seen this formulation a lot already. So the new weights are equal to the old weights plus the learning rates times something that we call delta W. And we've seen already a lot of examples how to calculate the delta W. And the learning algorithms that we've seen so far, they differ in the way how they calculate delta W. Okay. Yeah?
Is it possible to combine? Yes.
Yeah?
Possible to combine the perceptron with the Oyer's algorithms?
Mm-hmm. Again? The audio was a bit broken. I just heard Oya and perceptron.
I have asked if it's possible to combine the both algorithms.
Combine Oya's learning algorithm and perceptron?
Yes.
Yes. You can first do a linear layer that's trained unsupervised, and then you could do the rest of the training supervised. So that's in most practical application, you first have to reduce the dimension of input space, right? And then you do learning in the PCA space, for example. Yeah, but uncorrelated.
Okay.
Yeah.
Thank
and
you.
honestly, this depending on if you have bottleneck architectures in your multi-layer perceptrons, they usually perform kind of PCA.
Oh, okay.
Yeah.
Yes.
So we look at different principles. So you can apply them individually or together, and there are also extensions to all these concepts that we are introducing here as basics, right? And but they are the starting point to understand how more complex applications work. Okay, so so remember what we know already. for supervised learning. So we have the perceptron, this function h, right? That's given here, or the delta w, right, for the perceptron is calculated as the target value minus the current output of the neuron times the input value, and we divide it by 2, right? This is the formulation we introduced for the perceptron learning rule. For the eta line, this function h corresponds to the negative gradient of quadratic error evaluated for x for xq evaluated for the current weights w prime, right? So these are the 2 update rules that we introduced in chapter 3, and we had another update rule, as already mentioned, an unsupervised one, Oyas and Senger's learning rule respectively, right? But this is unsupervised, okay? So here we multi-layer perceptrons are supervised architectures, and the error back propagation especially. Okay. So this is how this all relates, right? So we are not doing something different right now. We are just using the concepts we already know, and we extend it to multi-layer networks. Okay. So the classical approach to learn is, what we are doing, we are defining now an error surface E over the space of network parameters. And the network parameters are the weights, Vi and Wj. They are both weight sets are parameters of the model. And the error surface is defined over the space of the combined weights, right? So it's a pretty huge space. So, for example, what the way to go to define this error surface is, for example, and that's what we hear in the classical form, using the quadratic error. So for each training sample, XQ, we can define an error surface, EQ. And the error surface is given. So we are summing over the outputs of the network, and we subtracting the target, the current output of the IS neuron from the target value of the IS neuron, and we square it, right? So this is the error for a training pattern XQTQ. Yeah? And as for the perceptron, we are now iteratively minimizing these error surfaces for individual training patterns. So this is basically the same approach that we did also for eta line. It's a mixed formulation. So we have pattern based, so we focus on one pattern, XQTQ, and we are using the quadratic error that we introduced for eta line. For eta line, we dealt with linear error function because we assumed that the activation function of the eta line is linear for the training phase. However, here we do have, if we apply this for the multi-layer perceptron, the objective function, this error function, is no longer linear. And we also have to learn many weights of many neurons simultaneously. Okay, that's the difference. First, we cannot get rid of the nonlinearity because it's built in the hidden layer. And we have lots of weights. We have weights in the output layer and we have weights in the hidden layer. So the approaches now that we are taking is the same as for Ada-line. We want to minimize the gradient of the error. We want to minimize the error function, and we want to do this by gradient descent. So let's focus first on the weights of the neurons in the output layer. How to perform gradient descent for the weights in the neuron, in weights of the neuron in the output layer. So this is the general form. So the output, the individual weight in the output, Wji, is updated by using the current weights of the nth iteration step and adding delta Vji multiplied by the learning rate alpha. So this delta Vji is given by the negative gradient of the quadratic error function for training sample Q that we formulated on the previous slide, and we take the partial derivative with respect to Wji. So this is the same formulation we've seen already in chapter 3. So we can formulate it, we can plug in the quadratic error function, and this is the partial derivative that we have to calculate. And here in this figure, I tried to depict. So what we are doing here, we are now updating one weight of one neuron in the output layer, right? So, and as you can see, this weight, Wji, is just part of one of the summings of the sum here over I. Okay? So this makes this problem very similar to what we already did for Ada-line. So we have I Ada-lines here in the output layer. Okay, so this is the next slide is basically nothing new to you because we have done this already for the Ada-line model. So calculating the partial derivatives here is given step by step. We can redo this and maybe you remember what we already did. So the weight vector update Wji is the negative gradient of the error function EQ with respect to Wji, and this is minus 1/2 times, because this doesn't contain any variable, right? Times the partial derivative of the sum over the output neurons, where we subtract the target value and current output squared. And as I okay, so where is the Wji? The Wji is part of the current output of one of the neurons. So it's part of this of one of the functions ym of x of q, right? So I substituted here the ym just by the way we calculated. So the output of the neuron M here is calculated by the weight vector of the neuron M, right? So we have the sum over all the weights connecting this neuron to the neurons in the hidden layer. So we're starting from L equals 1 to J, which is the dimension of the hidden layer. And we are multiplying the weight times the output of the hidden neuron. Okay. So, and now we can start to do the partial derivative. Okay. Since this I here is fixed, it's a fixed number. The only, and let's go back here. So there's only one output value here which contains VJI. And this is exactly the neuron I in the output layer. So we have the target value for the neuron I, and we are subtracting the output, the current output of this neuron, right? So that's the first step that we are taking. All the other terms here in this sum are considered to be constant. Okay. Because they don't contain WJI. However, we have to apply chain rule. And we have to take the partial derivative of this term here. How we calculate, or because WJI is part of the sum here, right? So we have to apply chain rule, and we have to take the partial derivative of minus, be aware of the minus, the sum from L1 to J, VLJ times SL. Okay. This is again not very complicated because only one of these terms here, summings of the complete sum, contains WJI, right? The term where L is equal to J, right? And then what we are left with is, or what's left is the output value of the J's neuron Sj. And if you may wonder what happened to the negative sign here, we have a negative sign here in the front. So minus times minus gives plus, so this disappears. So that's basically the partial derivative of for one weight in the output layer, right? And again, in the end, I collapse the calculation of the output value of neuron I to to the original term. So this is the output value of neuron I given input pattern XQ. We have the difference to target value, so TIQ minus YI of XQ times the output of the J's neuron in the hidden layer. That's a partial derivative we already calculated. Using a one index less, I guess in the for the not I guess I know for the other line, but in principle that's the same. All right. Questions?
Professor,
Yeah.
one question. I understand everything, but only one question. The third step by our calculation, we take the second term where it's minus the J neurons, the
Minus the sum over.
yeah. Can you explain me only this term again, and then it's good, please?
Where this term comes from?
Yes, genau. Yes.
This term is equivalent to that term.
Okay.
Right?
I see it. Yes, I see it.
Okay.
Yes.
So this is, I mean, here we got rid of the square, right?
Yeah.
Okay.
Yeah.
So this is chain rule.
the gradient. Yes, thank you.
This is applying the chain rule.
Yeah.
Because we haven't done anything here to the sum, right?
Mm-hmm.
So we have to consider the sum next.
Mm-hmm. Thank you.
Mm-hmm.
And what about the summation?
The summation is so
No,
this
the AM equal to 1 to I.
m equals 1. Okay. Right. Right. Okay. So because look at, I mean, this gives you good so this is the direction in space we are looking at, because we have multivariable function, and these are the variables, right? And we are focusing on the direction yji, and as you can see, yji is only used here for calculating the output yi, right? Do you see that?
Yeah.
I hope this helps a bit. Understand why all these other things vanish. Okay? In this case, we will see what happens when we move on to the hidden layers. Okay, so let's move a step further. So how do we update the weights of the neurons in the hidden layer? Again, the basic iterative formula stays the same. So we are updating the weights WKJ, which are now the weights of the neurons in the hidden layer, right? This is how we term them, okay? So we are updating them by using the value we calculated for the weights in iteration step number n, and we are adding the delta WKJ weight by a learning rate. Okay. So how do we calculate the delta values for the weights of the hidden neurons? The approach is basically the same as for the weights of the output neurons. So we take the negative gradient of the error function with respect to the individual weight WKJ. That's the direction of space, direction in space that we are considering. So, and again, we are ending up with this expression here. So we have to differentiate the quadratic error function for training pattern XQ. Right? So here in the figure, I tried to depict the situation for the weights of the hidden layer. So we focus on this particular weight, WKJ. And as you can see, this weight is used to calculate all the outputs of the network. You see it? So it's part of the calculation of all the outputs. So it occurs in all summons of this sum here. So what we can expect is that the partial derivative for the weights of the neurons in the hidden layer is going to be a bit more complicated. And this is how we do it. So as you can see, it looks slightly more complicated than what we did for the neurons in the output layer. So let's start. The first step is basically the same as we did, except that we now have a W parameter here in the derivative. So this is again our sum over the output neurons, the derivation of the target value and the current value of the output neurons. Let's go to the next line. So when we compare this to the sum here, what happened next here in the output neurons? We got rid of the sum because the V values are only only occur in one of these sums. That's not true for the hidden layers. So what we do, what we get here, we get the sum over the neurons in the output layer from m equals to 1 to I, and we get the difference between the target value and the current output value of the mth neuron. And what we have to consider is, because Wj is part of calculating the output of the neuron here, of the neuron here, SL. So we will get a term that's called minus Vjm, right? So the first step we take is we get rid of the square. So we have 2 times the difference between target and output value of the neuron. And then we have to consider, we have to apply chain rule to what's in the brackets here. And that's the target value minus how we calculate these output values. That's the sum over the neurons, over the dimension of the hidden layer, L equals 1 to J. And we consider the weights of the neurons in the output layer times the output of the Lth neuron in the hidden layer. And be aware, this is part of this edgy brackets here. So this is one thing. So when we look at this and we get the partial derivative of this term here and get this m times, we always have to consider the weight Vjm, because this connects the nth neuron with the j's neuron in the hidden layer, for which weight we are looking here, right? So this is the first step, right? So, but we are not done, because the weight Wkj is part of, or is included, or is part of how we calculate the output of the j's neuron. Let's look here. So what we did, we've done this part here for the output neurons, and now we focus on the hidden neurons, right? And Wkj is part of all these output neurons, but it's only part of the output of the j's neuron in the hidden layer. So this is Sj, and we have to get the partial derivative of the function Sj, which is given as the sigmoid activation function applied to the inner product of the weight vector of this neuron j times the input. That's written here, right? So this is the activation function applied to the inner product of the weight vector of the neuron j and the current input value. All right. Okay. So when we focus on this boxed term here, we do see this is a nonlinear activation function. So getting the partial derivative for one with respect to Wkj involves applying the chain rule for next time. So first we have to get the derivative of the sigmoid transfer function, which is f1 prime, right? Applied to the same argument as we have here, the inner product of the weight vector of the j's neuron transpose times x cubed. And since this is first calculating the derivative with respect to the activation function, we again have to apply chain rule. And now we have to apply, we have to get the partial derivative with respect to WKJ for this inner product. And that's simple because there's only one of the terms here, one of the W's that's equal to WKJ. All the other terms here are considered to be constant. So what we end up with is XKQ, right? Because this is the factor that's associated with the weight WKJ. If we put this all together, we end up with this formula how to calculate the weight vector update for the weight WKJ. So this means we have to evaluate the derivative of the sigmoid activation function for the weight vector Wj transpose times xq, the inner product, times the input xkq, the input to the cave neuron of the hidden layer, times the sum over the output neurons, right? We are summing here over the output neurons, the deviation of the target value and the current output value weighed by the weight Vjm of the output. Okay, so this was how we calculate the weight vector update for neurons in the hidden layer. This is technically a bit demanding, but it's not really complicated. Usually you will find a more compressed version of this, but I think it's useful to go through it step by step. All right. Questions?
Do we need to practice this derivation for the exam purpose?
Can you repeat? It was a bit louder.
Do we need to practice this derivation for exam purpose?
This one is relevant for the exam. I expect you, for those of you who want to have grades in the upper range, this is relevant. Okay? This is, yeah? Come up with the derivation or come up with the weight vector update for the weights of the neurons in the output layer.
Okay.
This is, you don't have to reproduce the partial derivatives for the weight vector update for the weights in the hidden layer. Okay?
Okay. Yeah.
Okay?
Thank
Don't
you.
start to memorize these things, this slide, right?
Yeah.
It's important that you understand it. I mean, it's twofold. I mean, first of all, you should see it. I mean, it's not really straightforward, but it's doable. It's understandable, right? So you don't have to be afraid of these things. But it's a bit complicated, okay? So this is what, yeah? Because when you use the software tools, right, the packages, right, they all do that, yeah. And you have to have a feeling about what they do, what's done in the background, okay?
Okay.
Mm-hmm. Okay. So any further questions? If there are no further questions, I want to move on with the bad news. I mean, it's not really bad news. I mean, it's bad news in terms of computational efficiency. So when we look at the product here, how do we update the neurons or the weights of the neurons in the hidden layer? We see that we have to calculate the derivative or evaluate the derivative f prime of the sigmoid transfer function. And as I mentioned in the beginning, this involves evaluating an exponential function and so on. And this is computationally very expensive, right? So since we have to evaluate the derivative of the sigmoid activation function, this will get a bit computational numerically expensive. So this is critical in numerical terms, but there are good news. We don't actually have to calculate the derivative because the sigmoid activation function, here you see, this is an exponential function we have to evaluate. The derivative of the sigmoid activation function at 1' offset can be calculated by using the function value of f1. So the derivative of the sigmoid is given by the derivative by the sigmoid itself times 1 minus the sigmoid itself. Okay, so we don't have to calculate the derivative. We can use the outputs of the neurons in the hidden layer to calculate the derivatives, but we have to store them. That's but that we do anyway. Okay, so you can prove this, right? You can prove this equation. Try to show that the derivative of the sigmoid function is equal to the sigmoid function itself times 1 minus the sigmoid function. That's nothing too complicated, and try it yourself. Try to get a bit, try to practice a bit with all the math. Okay, so as I said already, we don't actually have to calculate the derivative. We can use the output of, or we can use the sigmoid activation function itself. And in our network, just for the notation, the derivative of the sigmoid transfer function apply or given the argument of the transposed weight vector of j times xq is equal to sj, the output of the j's neuron, times 1 minus sj. So the output of the j's hidden neuron times 1 minus the output of the j's neuron. Okay? And this is what we are actually already calculating in our network. So we can update the formula that we derived here by just substituting what we found out about how we can calculate the derivative of the sigmoid transfer function. So the effective weight vector update for the neuron in the for neurons in the hidden, for the weights of the neurons in the hidden layer, delta wkj, is given by the output of the j's neuron in the hidden layers times 1 minus the output of the neuron in the j's layer times the input, the input, the case input of example q times the sum over the error bit for the individual output units weighted by the weights of the neuron J and the output. That's how we effectively calculate the uptake of the neuron, of the weights of the neurons in the hidden layer. That's something that's quite important for application and getting efficient training. Otherwise, you wait forever. But this means that you have to store the output of the neurons in the hidden layer for the purpose of doing the weight vector update, right? Or the weight update. Let me briefly summarize what we've heard so far. So the problem, or now we want to consider problems that are definitely nonlinear separable. So we want to consider nonlinear separable data sets. The multi-layer perceptron, for short it's MLP, is a fully connected multi-layer feed-forward architecture with at least one nonlinearity in the hidden layer. Okay, so this is again a figure depicting the architecture. So we have the inputs x1 to xk. We have our neurons in the hidden layer, which are characterized by the signal activation function. The output of neurons in the hidden layer is calculated by the individual weight vectors times input data. And we are relaying this input to the neurons in the output layer by multiplying it again with weights wji. And we are getting an I-dimensional output layer. The activation function in the output layer is usually considered to be linear, at least for the moment we do that. Okay. So we have now derived a supervised learning algorithm for this architecture, and we assume the training data. So we have pairs, Q pairs of input-output data, XQ, TQ. We use the approach to minimize the quadratic error, and we did this in a pattern-based fashion. So we considered, or we are minimizing the quadratic error for an individual training pattern Q that we selected. Q is arbitrary but fixed, and this is the formulation of the error function that we are minimizing by the partial derivatives that we derived. The learning rule that we came up with for gradient descent is given here for the output layer. That's the general formulation of our iterative update, and the specific calculation of the weight vector update delta Vji for the neurons in the output layer. And here we have the formulation of the weight vector update of the neurons in the hidden layer. Okay, that's what we've done so far, right? Okay, and to other questions in the meantime. You had some time to think about it? Okay. So now we can formulate the error backpropagation algorithm, also known as short backprop. So this is again an algorithm formulation. So And we've seen structograms already, so this is nothing new to you. So what we start with is an initialization phase. So first of all, since we have an iterative approach, we have to initialize our variables. The weights in the hidden layer, the weight vectors of the hidden neurons, and the weight vectors of the output neurons. And of course, this includes the bias values. We have to choose a learning rate alpha. This is a hyperparameter of this algorithm. This is not a parameter that we are optimizing, that's a hyperparameter we have to choose. Okay? And usually we have to initialize our iteration counter, but that's more or less obvious, right? That's pretty obvious. So what we do is, for the full learning algorithm, the first thing we do is after we've done the initialization, we select a training pattern, XQTQ. We do this randomly. This was not so important for the perceptron, where we had a pattern-based learning algorithm. This was also for the ADA line. We used the error function over all training sets, so we didn't have to do this step. But here we have to select the training pattern randomly. What we do next? The next thing that we do is we calculate the output of the hidden neurons, Sj, for the nth iteration step. When we have calculated the output of the hidden neurons, we can calculate the output of the output neurons, yi, so the values yin, so the complete output of the network. So what we've done by these two loops, right, and we do this for all the neurons in the hidden layers and then for all the neurons in the output layers. What we've done by these two loops, this is we propagated the selected input pattern through the network, and we calculated the current output or the output of the network for the current input pattern. Right? So this is called forward pass because we are propagating the input all the way through the network and to calculate the current output. Okay, I now switch to the next slide because it didn't fit on one slide. So here we go. So we've been through the forward pass. Now we have to do the weight vector update, and we do it the other way around. The first thing we do is so we do it the other way around. The first thing we do is for all the weights in the output layer. So we are going through the index I for all the output neurons, and we are considering all the weights of the output neurons from all the J hidden neurons, and we calculate the weight vector update for the weight Vji, which is given by the formula we derived previously. I don't want to read it again. We update the weight of the neuron I that we are currently considering, the weight J of the neuron I, by using the learning rate and the calculated delta value. And as you can see here we are using the output of the neurons of the hidden layer. So we have to store these outputs. Okay, so we do the weight vector update for all the weights of the neurons in the output layer, and then we go back to the neurons in the hidden layer, and we do the same for all the weights of the neurons in the hidden layer. And as you can see again, also here we do need the output of the hidden layer Sj in the current iteration that we calculated in the forward pass to calculate the update of the weights of the neurons in the hidden layer. And so we are updating the weights, right? And then we update our iteration counter. We move to the next iteration. As you can see, we are going back through the network from the updating the weights in the output layer and then updating the weights in the hidden layer. So this is why this is called backward parse. And as you can see, and this is depicted quite nicely here in the structogram. So what we are actually doing, here we are calculating the current output of the neurons yi, right? And here we take the error, the difference or the deviation of the current output and the given target value, and we propagate it back through the layer. And this is why this algorithm is called error back propagation algorithm. Okay? So the error back propagation owes its name on the one hand to the forward pass. That's what I tried to explain. So the input XQ is propagated through the hidden layer of the network, and the current outputs YI are calculated. So the next step is that we do some supervision. Yeah. We compare the actual output value YI with the target value TIQ, right, residing in this error. Okay, this is the supervision part, when you remember what's the difference between supervised and unsupervised learning. And that's what we get here. So we have the supervision, and then we propagate this error back through the network, and we do weigh this error. And the weights are derived through this, through the process of partial derivation, right? So backward. So we start with the output layer, and we successively propagated back to the first hidden layer. We only have one hidden layer here in our example. That's fair enough for the moment, right? But you can imagine then that you can do this several steps. Okay. Questions, because we now finished the first points, and the next thing that we do is we move on. So next time we will move on to the XOR problem and the simple regression problem, and see how learning, how these types of the multi-layer perceptrons learn more complicated functions. Questions? No? Okay. So next week, I think we are splitting the lab groups again. This was just an exception this week that we had only one lab. Next week, there will be a lab on Monday, and an exercise on Monday, and an exercise on Tuesday. So we have split groups again. But this will definitely be won't be in-person labs on Monday, right? Just to announce this already, because I can't imagine that we are allowed to do in-person teaching. Okay. So if there are no questions remaining, I made a comment on what's relevant for the exam and what's not relevant already. Thank you for the question. And I think, yeah, enjoy the rest of the week. And see you next week, Monday or Tuesday.
Thank you.
Excuse me. Do we use the old link when we join the lab on
Okay,
Tuesday?
yeah, maybe this is a good hint. Today we use different links because I mean, the reason was I would have liked to give you a longer Christmas break. But given the date of the exam, which is mid of February, I thought we cannot waste the slots today, because my goal is to finish early so you have enough time to learn for the exam. Okay? So therefore I introduced this additional slots. But as it looks like at the moment, we are finishing early, maybe, yeah. So prior to the last week of the lecture term, and so next week the links you used before Christmas will work again, right? So you won't receive any further additional links. Yeah.
Okay. Yeah. Thank you.
Okay. Bye bye.
Bye.
Choose. Bye.